Hello everyone, welcome to the course Nature and Properties of Materials. In week 9, we'll have a summary session. So whatever all the 8 weeks that we have gone through, we'll just summarize that. So welcome to the course Nature and Properties of Materials. In week 9, we'll have a summary session. This course is offered by Professor Bishop Bhattacharya and Department of Mechanical Engineering, IIT Kanpur. And I'm TA Alka Jangid from IIT Kanpur. The course is Nature and Properties of Materials. So in first week, we went through basically material classification, and so the 5 general classes of materials are metals, non-metals, ceramics, polymers and composites. There are other classes as well, such as smart materials and others, but these are the classes that will be studying in this particular lecture. So in case of metals, you have 2 types again, subcategories, ferrous and non-ferrous. In case of ferrous, you have materials which are based on iron. So iron, steel, cast iron, all those have iron as the main metal. Next is non-ferrous, in which all materials other than iron consisting will be in non-ferrous. So copper, aluminum, titanium, gold, silver and tungsten. Next is non-metals. So in non-metals, you'll have materials which are not metals. So these are these can be in different physical states. So it can be in form of gases such as hydrogen, helium, nitrogen and oxygen. In liquid, it can be bromine. In solid form, it can be carbon, phosphorus, sulfur, selenium and iodine. In ceramics, these are materials which can sustain very high temperatures, and these are mainly combination of metal and non-metal. So alumina, silica, silicon carbide, diamond, graphite, these are some of the ceramics. Next is polymers. So it consists of wool, silk, polyethylene, PVC, nylon and bakelite. In composites, you have materials which are mixture of these categories. So wood, concrete, fiberglass, carbon fiber reinforced polymers and glass fiber reinforced polymers. Firstly, metals. So metals are characterized by following properties. In case of physical properties, they have good electrical and heat conductors, and they are malleable, so they can be beaten into thin sheets. They are also ductile and can be stretched into thin wires. They possess metallic luster. So as you can see, all these metals, they have metallic luster, and they are solid at room temperature except mercury. And chemical properties include they usually have 1 to 3 electrons in their outer shell, so they lose their valence electrons easily. So that's why these are good conductors of electricity and heat. These also form oxides which are basic, and these are also good reducing agents because they lose electrons, and they have lower electronegativity. So electronegativity meaning they have tendency to attract electrons, so they have less of that. So these are some of the examples of metals: cast iron, wrought iron, aluminum, steel. So out of these cast iron, wrought iron, steel, these are the alloys, not pure metals. Pure metal is aluminum, zinc, copper, lead, tin, titanium. Brass and alloy steel, carbon steel, these are again alloys. Next is non-metals. These are characterized by the following properties. So in case of physical properties, they are poor conductors of heat and electricity, and they are brittle if in solid state, and they are non-ductile, and they do not possess metallic luster and transparent as thin sheets, and solid, liquid and gases at the room temperature. So these are almost opposite to the what we saw in case of metals. Next is chemical properties. So they usually have 4 to 8 electrons in their outer shell, so they gain or share valence electrons easily, and they form oxides that are acidic, and these are good oxidizing agents and have very higher electronegativity. These are the examples. Carbon is one of the non-metals. Next is ceramics. So ceramic materials are inorganic materials made from compounds of metal and non-metal, and they are formed by the action of heat and subsequent cooling, and they are brittle in nature and they are good insulator of heat and electricity. There is exception to this, so graphite is good conductor of electricity and heat, and they are excellent they have excellent compressive strength, while in tension they don't show good strength. So these are some of the applications of ceramics in making roof tiles, bearings, pottery, ceramic coated turbine plates, etc. Next are polymers. So a polymer is a large molecule composed of many repeated subunits. So these can be natural and these can be synthetic as well. So in case of natural, you have shellac, amber, wool, silk and natural rubber, while in case of synthetic, you have synthetic rubber, bakelite, neoprene, nylon, polystyrene, polyethylene, PVC, polyvinyl chloride, etc. These are some of the applications of polymers. Next class is composites. So two or more constituent materials with significant different properties, which are combination, produces a material with characteristics different from the individual components, and the individual components remain separate and distinct within the finished structure. So these fibers and matrix combined will make a fiber reinforced matrix composite. So between this fiber and this matrix there will be defined interface. Next is mechanical properties. So firstly we start with the stress strain curve. So in this case stress is the internal resistance force per unit area acting on a material, and it uses the original cross section area of the specimen, and it is also known as engineering stress or conventional stress. So stress formula can be given as force per unit area, and unit will be Pascal or Newton per meter square. So this is your initial cylindrical specimen, and initial is with the test, and if you are applying tensile type of loading, then the final length will be increased. So L will be your final length. And in case of compressive, you will see final length will be shorter. Then next is strain. It is defined as the change in length per original length, per unit original length. It is unitless and also known as engineering strain or conventional strain or normal strain. So its formula can be given as delta L upon L naught. Sometimes strain is also expressed in microstrain. Next is Hooke's law. So within the elastic limit up to low strain values, the stress sigma is directly proportional to strain, and the behavior of the solid is linear elastic, and the constant of proportion is called the elastic modulus. So sigma is proportional to epsilon, and the proportionality constant will be elastic modulus, capital E. And it also holds good for stresses and strain in simple compression, and in the same way for shear stress as well. So in case of shear stress, tau is proportional to gamma, and the proportionality constant is shear modulus, and the pressure is proportion to the negative of dilation, volumetric strain, because positive pressure causes a shrinkage of volume. Hence P equals to minus K times delta V upon V, where K is the bulk modulus and all three modulus, they have same dimension as that of stress. And this is the stress strain curve. So initially it is proportional to the stress is proportional to strain. So this is linear type of behavior you will be seeing up to this particular point. After that there is permanent deformation occurring. So initially there is strain hardening. As you keep on increasing the stress, your strain increases, and after this necking point, which is ultimate tensile strength, this stress goes down, and finally the material fractures. Then there is elastic limit. It is the greatest stress that material can withstand without any measurable permanent strain after the unloading. And yield strength is stress at which a material begins to deform plastically, and it is determined by the stress corresponding to the intersection of the stress strain curve and a line parallel to the elastic line offset by a strain of 0.2%. And the tensile strength or ultimate tensile strength, it is the maximum load P max divided by the original cross sectional area A naught of the specimen, and the elongation can be given as final length minus initial length divided by initial length times 100, and percent reduction in area can be given as final area minus initial area divided by initial area multiplied by 100. Next is true stress, true strain. So true stress strain curve gives a true indication of deformation characteristics because it is based on the instantaneous dimension of the specimen. And in engineering stress strain curve, stress drops down after necking since it is based on the original area. And in true stress strain curve, the stress, however, increases after necking since the cross sectional area of the specimen decreases rapidly after necking. The flow curve of many metals in the region of uniform plastic deformation can be expressed by the simple power law, which can be given as sigma T equals to K times K multiplied by epsilon T power N. So N is your strain hardening exponent, K is strength coefficient, and N can be 0 for perfectly plastic solid, N can be 1 for elastic solid, and for most metals it is between 0.1 to 0.5. So between this particular area, this is followed. Next properties are ductility and brittleness. So in case of ductility, it measures the degree of plastic deformation that has been sustained at fracture, and the strain sustained at the fracture, strain at failure is more than or equals to 0.05, or the percentage elongation is greater than 5%, then your material will be ductile. So as you can see, if your ductility meaning this percentage elongation at fracture, if this is very high, then your material will be ductile, and if it is less, then it will be brittle. And these materials will be having well defined yield point. In case of brittle materials, so a material that experiences very little or no plastic deformation upon fracture, and the strain at fracture is 0.05, lesser than or equals to 0.05, or percent elongation is less than 5%. These do not exhibit an identifiable yield point. So these materials, you can see this material doesn't show any kind of necking, so this material is brittle fracture. While in case of ductile fracture, you will be seeing this type of necking phenomena where voids will nucleate first, then these voids will lead to coalescence, then finally crack will from this coalescence void there is neck will be propagating at particular angle, and then this specimen will get separated. Next is resilience. Resilience is the capacity of material to absorb energy when it is deformed elastically and then recovers same upon unloading. The modulus of resilience, which is the strain energy per unit volume required to stress a material from an unloaded state up to the point of yielding. The SI unit is joule per meter cube, and the resilience can be given as half times sigma y, which is yield strength multiplied by yield strain, epsilon y. Now this epsilon y can be written in terms of this yield strength and elastic modulus. These are the properties we generally know, so it can be written in terms of sigma y square upon 2e, and this half is because this is a triangle type of shape forming with using these two equations. So sigma y times epsilon y and half of that particular thing. So for resilient materials, they have very high yield strength and low modulus of elasticity. For example, beryllium, copper, and these materials which are resilient, they are used in making spring. Next is toughness. So it is the measure of the ability of a material to absorb energy up to fracture. So in previous one you had resilience, so the area will be only up to yield point, right? So after this only elastic part is included, and here you include all area up to fracture point. Okay, so it is the measure of ability of a material to absorb energy up to fracture, and it is represented by the total area under the stress strain curve up to the fracture point. The brittle material has comparatively high yield and tensile strength but low toughness due to the lack of ductility, and the ductile materials are always tougher compared to the brittle ones. So as you can see here as well, brittle material has lower area under the curve compared to this ductile material. Next is impact testing. So in these tests, load swings from a given height to strike the specimen, and the energy is dissipated in the fracture is measured. The metallic samples tend to be square in cross section, while polymeric test specimens are often rectangular. The factors which affect impact energy, they are for a given material, the impact energy will be seen to decrease if the yield strength is increased, and the notch serves as a stress concentration zone, and some materials are more sensitive towards notches compared to others. Most of the impact energy is absorbed by means of plastic deformation during the yielding. Therefore, factors that affect the yield behavior and hence ductility of the material, such as temperature and strain rate, will affect the impact energy as well. So this is the for various types of materials. So for ceramics, impact energy is very less, this impact strength, and for metals it is highest, then for polymers and for composites it is in between these. Next is hardness. So it is the measure of a material's resistance to localized plastic deformation and a small indentation or a scratch. The advantages of hardness testing: it is simple and inexpensive, and no special specimen preparation is needed, and the apparatus is relatively cheaper. This method is also non-destructive, so small indentation is the only deformation that occurs, and other mechanical properties like tensile strength and fatigue strength can be obtained from the hardness data. Next is various types of hardness tests. So first is Mohs scale. So it is based on the ability of one material to scratch another. So the hardness is measured on a scale from 1 to 10, 1 being the softest, 10 being the hardest. In case of macro hardness test, you have Rockwell hardness test, Brinell hardness test, and Vickers hardness test. In micro hardness test, you have Neupen, Vickers micro hardness test. In case of Vickers, you by changing the load, you can go between macro hardness and micro hardness test. And these are various materials and their absolute Mohs hardness. So for talc it is 1, and for diamond it is 1600. So it is the Mohs hardness will be 10 while absolute hardness will be 1600. So you can be asked these particular, you should remember these particular Mohs hardness for these minerals. Next is other tests such as Brinell, Vickers, Knoop and Rockwell. So in case of Brinell, you have 10 mm steel or tungsten carbide ball. So for this, loads used are 500, 1500 and 3000 kg, and formula that's used is this one. And for Vickers, you have diamond pyramid with 136 angle, and the load used is 1 to 120 kg, and the Vickers hardness is the formula used is this one. For Knoop, it is diamond pyramid and the load is between 25 gram to 5 kg. And for Rockwell, you have different types of indenters. You can have diamond cone for ACD scales and 1/16 inch diameter steel wall. For BFG scales, for E scale you have 1/8 inch diameter steel wall. And the loads used are 60, 150 and 100 kgs. And the hardness numbers that I used are formula are 100 minus 500T and 130 minus 500T. Next is creep. So creep is the permanent deformation under constant load over a period of time. So it is dependent on temperature. A creep test involves a tensile specimen under a constant load maintained at a constant temperature. And at relatively high temperatures, creep appears to occur at all stress levels, but the creep rate increases with increasing stress at a given temperature. Applications. So studying material behavior at elevated temperatures such as turbine blades, nuclear reactor components, jet engines, heat exchangers, etc. And creep occurs in 3 stages. Primary stage being it occurs at the beginning of the test, and creep is mostly transient. Secondary stage, in this case creep rate roughly steady, and in tertiary stage creep rate begins to accelerate as the cross sectional area decreases due to the necking followed by failure. So this is the creep curve. Next is periodic table. So this is the, in case of columns, you see these materials will have similar type of electronic structure and also similar properties. So, and when you move to this side, the electronegativity will increase, and in this side electropositivity will increase, and in this case it will readily give up electrons to become positive ions. Cesium will be the most electropositive, while in this side it will readily acquire electrons to become negative ion, and the fluorine is most electronegative. Now the types of bonding. First is primary bonding. These are relatively strong, and these materials melt between 1000 to 4000 Kelvin. And examples are covalent bonding, ionic and metallic bonding. Next is secondary bonding. These are relatively weak, and these materials melt between 100 to 500 Kelvin. Examples include van der Waals bonding, hydrogen bonding, dipole-dipole bonding and others. First is ionic bonding. It is found in compounds which are composed of both metallic and non-metallic elements. The large difference in electronegativity is required, which means bonding occurs between elements situated at the periodic table's horizontal extremities. It requires electron transfer to achieve stabilized outermost electronic configuration, and the bonding forces are Coulombic, and the attraction between opposite charges will be there. Examples include NaCl, AgCl, CSCl, zinc sulfide, calcium fluoride, lithium fluoride, magnesium oxide, and alumina. Properties include ionic bonds, which are non-directional because the magnitude of the bond is equal in all the directions around an ion, and it has higher melting point because of large bond energy, typically 600 to 1500 kg per mole, and these are often hard and brittle materials. And ionic solids are good insulators of electricity in their solid state and good conductors of electricity in their molten state. Next is covalent bonding. So it is stable electron configurations are obtained by the sharing of electrons between adjacent atoms. The covalent bond is directional in nature, means it occurs between specific atoms and only in the direction between one atom and another that participates in the electron sharing. Number of covalent bonds for a particular atom can be given as 8 minus n, where n is the number of valence electrons. Examples include non-metallic molecules such as hydrogen, fluorine, and chlorine gases, and molecules containing dissimilar atoms such as methane, water molecule, HNO3, HF, etc. Elemental solids such as diamond, silicon, and germanium. Solid compounds such as gallium arsenide, indium antimonite, and silicon carbide. Polymers, they can also contain secondary bond. Next is metallic bonding. It is found in metals and the alloys. Metallic materials, they have at most 3 valence electrons which are not bound to any particular atom in the solid, forming an electron cloud. Rest non-valence and atomic nuclei form ion cores, which can be seen here in image, and having a net positive charge. And there is a force of attraction between valence electrons and metal ions. These free electrons, they act as a glue to hold the ion cores together, and the metallic bond imparts properties such as strength, malleability, ductility, luster, conduction of heat, and electricity. Next is hydrogen bonding. It is the strong dipole-dipole attractions which involves molecule with OH, NH, and FH groups. Examples include water expands upon freezing. So in case of solid ice, each water molecule participates in 4 hydrogen bonds. So as you can see here, the hydrogen bonds keeps molecules apart, thus relatively open structure. Hence ice has a lower density compared to liquid water, and it floats on the water. Next is van der Waals bonding. It is weak in comparison to primary bonding. Bond energy is of order of 10 kg per mole, and it occurs to some extent in all materials but is particularly important in plastics and polymers. The result from attractive forces between electric dipoles. So you can see this is dipole-dipole. Next is bonding in materials. So the major classes of materials, first is ceramic. In this case you have ionic and covalent type of bonding, and this type of bonding, it provides it high bond energy leading to high melting temperature, large elastic modulus, and small thermal expansion coefficient. In case of metals, they have metallic bonding and they have variable bond energy and moderate melting temperature, and also moderate elastic modulus and moderate thermal expansion coefficient. In case of polymers, you have covalent and secondary bonding, and these have directional properties. Secondary bonding dominates, and small melting temperature is there, and small elastic modulus is there, and large thermal expansion coefficient. Next is crystalline solid. So a long range structure exists in which atoms are arranged into unit cells, and the unit cells repeat in a regular orderly pattern forming a lattice 3D. So directional properties will be there, and it will lead to provide them anisotropic nature. These have sharp melting points. Examples include gold, silver, alumina, etc. So here also you can see this particular direction and this direction, the atomic packing density is different. So these will be having different mechanical and optical and different properties in different directions. Next is polycrystalline metal, polycrystalline solids. So these are made up of an aggregate of many small single crystal, also called crystalline or grains. These across grain boundary, the orientation of the crystal changes, and the grains are usually 100 nanometer to 100 microns in diameter, and the polycrystalline materials have a high degree of order over many atomic or molecular dimensions. The polycrystals with grain that are less than 10 nanometer in diameter are called nanocrystalline, and most engineering materials are polycrystalline, and the properties may or may not vary with direction. Examples include common steel is polycrystalline, and if grains are textured due to rolling, then anisotropic. Otherwise, if grains are random, then it will act as isotropic. Next is single crystal. So in this case you will be having only one grain and there won't be any grain boundaries, and it is formed by uniform cooling of liquid material. These have high degree of order throughout the entire volume of material, and it is useful for application where grain boundaries are harmful. For example, high temperature deformation of creep resistance, as creep takes place by grain boundary sliding. Single crystal turbine blades, which are nickel based superalloy gas turbine blades, they can withstand creep at very high temperatures due to lack of grain boundaries. Some other examples include diamond and semiconductors. Next is amorphous solid. These are the atoms or molecules which are arranged in an irregular manner. They have no periodic packing and no directional properties. So they show isotropic type of behavior for most properties, and these occurs for complex structures and rapid cooling. So if you are taking an alloy system which has a lot of elements, more than 5, then if you solidify it, then it is more likely to solidify in amorphous state. And if you are cooling it rapidly as well, then in liquid state it has random packing. So it will, in solid state as well, it will have random packing and leading to amorphous state. Examples include glass, plastic, rubber, etc. This is the silica structure SiO2, which can form crystalline as well as amorphous state as well. Next is unit cell. It is the smallest block or geometrical figure from which the crystal is built up by repetition in 3 dimensions. The fundamental grouping of particles which are repeating entities. Unit cell is the basic structural unit or building block of the crystal structure. A crystalline solid can be constructed from a unit cell plus translation operators. So this is the unit cell. If translating it along x-axis, it will give you 1D lattice, and the translating along y-axis as well, it will give you 2D lattice, and translating along z-axis will give you 3D lattice. Next is crystal system. So firstly, what is lattice? It is the array of points in space in which every point has an identical environment with respect to all other points. Basis is the single atom or group of atoms or molecules which are identical in composition and orientation in space. So if you put this basis, this atom at the lattice points, you will be getting the crystal structure. Okay, and these are the crystal systems: cubic, hexagonal, tetragonal, rhombohedral, orthorhombic, monoclinic and triclinic, and these are the axial relationships and interaxial angles as well. So these can be asked in questions in exam, so you should remember these relationships. For cubic it will be all will be equal and angles will be 90. For tetragonal and for orthorhombic, these will be angles will again be 90. For tetragonal, one axis will not be equal, and for orthorhombic all axes will be different. Next is Miller indices. So Miller indices are the designation of the planes and direction in the unit cell, and the number of indices will match with the dimension of the lattice or the crystal. Example, in 3D, the unit cell has 3 indices, namely HKL, and HKL represents a point, but no comma is used while representing indices. So these are various brackets that I used. So for this small bracket, there will be for individual plane, and for curly bracket it is used for family of planes, and for square bracket it is used for individual direction, and for this triangular bracket or caret bracket it is used for family of directions. Miller indices of a plane. So firstly you have to choose an origin O in the unit cell such that plane does not touch the origin and plane is closest to the origin. Then you have to mark intercepts from the chosen origin along x-axis as A, along y-axis as B, along z-axis as C. Then you have to take reciprocal of the intercepts 1 upon A, 1 upon B, 1 upon C. Then you have to modify the reciprocals, meaning you have to reduce the multiples. So if it is 2, 2, 2, then you can reduce it to 1, 1, 1. And if it is fraction, so if it is half 1, 1, 1, then you have to multiply it with 2, so it will become 1, 2, 2. So you have to eliminate the fractions, then put a bar above the negative integer in indices. So if there is -1, then you have to put bar on this 1. So I think it is given here. So similar to this, you have to put bar. Then place round brackets around the indices. In case of direction, you have to firstly create new origin O dash at tail if necessary, then label O dash and new axis x dash, y dash and z dash. Then you have to find the coordinates from tail at O dash to the head of the direction. Then you have to reduce multiples, eliminate fractions, use bar for negative and plus square bracket around the integer. So as you can see here, from O dash you are walking in x direction up to 1, in y direction as -1 because y is positive in this direction, so -1, and z 1, so 1, -1 and 1. Next is crystal defects. So any deviation from a crystal's completely ordered arrangement of constituent particles is called a defect or imperfection. The properties of materials are influenced by the presence of imperfections. The mechanical properties of pure metal change significantly when metals are alloyed. The classification, so these can be zero dimensional or point defects. So in this case you have vacancy defect, interstitial defect, substitutional defect, Frankel and Schottky defect. In 1D or linear defects you have edge dislocation, screw dislocation and mixed dislocation. In 2D, meaning planar defects, you have grain boundaries, twin boundaries and free surface. In case of 3D or volume defects, you have voids and cracks. Next you have vacancy defect. So when an atom is missing from its regular lattice site, it is called a vacancy, and it is impossible to create a material free from vacancy defects. The presence of vacancies increases the entropy or disorder in the crystal, and it decreases the density of the substance. The concentration of vacancies increases with increasing temperature, decreasing activation energy QV, the energy required for the formation of vacancies. So equilibrium vacancy concentration can be given as exponential minus QV upon KBT. Next is grain boundaries. It is the boundary that is separating the two grains or crystals having different crystallographic orientations in polycrystalline material, and the atoms near the boundaries are slightly disordered and have higher energy compared to those with the grains. In general, a grain boundary has 5 degrees of freedom. We need 3 degrees of freedom to specify the orientation of the grain with respect to the other, and 2 degrees of freedom to specify the orientation of the boundary with respect to one of the grains. Here you can see there are two types of grain boundaries: high angle grain boundary and small angle grain boundary, depending on angle of misalignment. Next is the metals. So classification of metals. Metals can be ferrous and non-ferrous. In ferrous, we have materials which are based on iron, so steel and cast iron. So steel will be consisting carbon less than 2.1 weight%, and if carbon is more than 2.1%, then it will be cast iron. Other is non-ferrous, which consists of aluminum, titanium, copper, bronze, etc. Next is again classification of steel. So steel can be classified into low alloy steel and high alloy steel. In low alloy steel you have low carbon steel, medium carbon steel and high carbon steel. So this will be consisting less than 0.25 weight% carbon, from 0.25 to 0.6 for medium, for high more than 0.6 up to 1.4 weight% carbon. In case of high alloy steel, you have tool steels, stainless steel, barraging steels and others. Next is low carbon steel. It contains less than about 0.25 weight%, called as mild steel. It is relatively soft and weak, and it has outstanding ductility up to 25% elongation and toughness, and it also has high machinability and weldability, and it is least expensive to produce. Tensile strength is up to 415 to 550 MPa. Applications include beams, channels, nut bolts, wires, tin cans, etc. Low alloy steels. These contain alloys such as copper, vanadium, nickel and molybdenum up to 10 weight%, and they have high strength and corrosion resistance than plain carbon steel, and tensile strength is up to 700 MPa. Next is medium carbon steel. It contains 0.65 to 0.25 to 0.6 weight% carbon. It is stronger than low carbon steels but of low ductility and toughness. It has good wear resistance, and the plain carbon steel tensile strength is up to 850, while alloy steel has 1900 MPa. Applications include railway wheels and tracks and gears and crankshafts. High carbon steel. It has 0.6 to 1.4 weight% carbon, and it is hardest, strongest and least ductile carbon steel. It can be alloyed with carbon and other metals to form very hard and wear resistant materials, so chromium, nickel, tungsten, molybdenum and vanadium. Applications include cutting tools, dies, saw, concrete drills, etc. Next is tool steel. So it is commonly used in drill bits and other rotating cutting tools. It can withstand higher temperatures without losing its hardness and toughness. Examples include 1841 high-speed steel, which consists of 18% of tungsten, 4% chromium, 1% vanadium, with a carbon content of 0.6 to 0.7%. Cobalt is high-speed steel. cobalt high speed steel, which has increased heat resistance, molybdenum high speed steel, which has molybdenum increases hardness and wear resistance, also a cost effective replacement for tungsten in tool steels. Next is stainless steel. So it is highly resistant to corrosion in a variety of environments, and predominant alloy consists of chromium, which is at least 11 weight%. Examples include 18-8 stainless steel, 18% chromium and 8% nickel. Applications include cryogenic vessels, food processing equipment, gas turbine parts, high temperature steam boilers, heat treating furnaces and nuclear power generating units. Next is cast irons. So in this case you have grey cast irons. So carbon content varies from 2.5 to 4 weight%. So this is the microstructure of grey cast iron, and these are the graphite flakes. So in this case graphite exists in the form of flakes. Graphite flakes give self-lubricating properties and vibration damping capability. And the strength and ductility are much higher under compressive loads, and tensile strength is between 120 to 280 megapascal. Applications include base structure for machines, heavy equipments that are exposed to vibration, white chilled cast iron which has no graphite, carbon in the form of carbide, and cementite is the hardest constituent of iron. It is formed by rapidly cooling molten iron. It is very hard, wear and corrosion resistant, and it is almost non-machinable, and applications include rollers and rolling mills. Next is malleable cast iron. It is formed by heating white cast iron between 800 to 900 degrees Celsius for a prolonged time in a neutral atmosphere to prevent any oxidation, and it leads to decomposition of the cementite, forming graphite in the form of clusters. It is highly shock resistant or tough, and the tensile strength is between 350 to 450 MPa. It can be hammered to small thickness. Applications include connecting rods, transmission gears, pipe fittings and valve parts. Next is ductile, nodular or spheroidal cast irons. It is obtained by adding a small amount of magnesium 0.1 to 0.8% to molten grey cast iron, which leads to the formation of graphite in the form of spheres. It has high fluidity, toughness and wear resistance, and high tensile strength from 400 to 900 MPa, good machinability and weldability. Next is strengthening mechanism in metals. The ability of a metal to plastically deform depends on the ability of dislocations to move. Thus, restricting or hindering dislocation motion makes a material harder and stronger. Some mechanisms to strengthen metals are as follows. So, grain refining, solid solution strengthening, strain hardening, precipitation strengthening, martensitic strengthening and composite strengthening. So, all these will be covered except these two. So, in case of martensitic strengthening, what happens? You are quenching your steel, and the austenite phase will be converted into martensite. So this martensite has very high hardness, so this will be providing strengthening to material. In case of composite, you are adding some reinforcement or some different second phases to material, which will be providing it strengthening. So first is grain refining. In this case, a fine grain material, the one that has small grains, is harder and stronger compared to coarse grained due to a greater total grain boundary area to restrict dislocation motion. So the Hall-Page equation that is used, that is sigma naught equals to sigma I plus ky upon under root t. Here your materials, sigma naught is the yield strength, Sigma I is the frictional stress opposing motion of dislocation. Ky is the extent to which dislocations are piled up. D is the average grain size. So the critical grain size, which is typically around 10 nanometer, the yield strength would either remain constant or decrease with decreasing grain size. This phenomena is known as the inverse Hall-Page relationship. So these are the grain boundaries. It will be providing some barrier to free movement of this dislocation. So if you are applying any force to this particular grain, then this dislocation will go and pile up here, and this will these grain boundaries, they act as barrier for these type of dislocation movement for any deformation. So this material will be having higher strength. Next is solid solution strengthening. So pure metals are almost always softer compared to their alloys, and adding another element that goes into interstitial or substitutional positions in a solution increases the strength. The impurity atoms, they cause lattice strain which can anchor dislocations. Thus alloys are stronger than pure metals. So here also you can see, as in copper, you are keep on increasing the amount of nickel, the tensile strength is keep on increasing, and the elongation percent ductility, it will reduce. So these are, as we know, tensile strength and ductility are always inversely proportional. So if you keep on increasing the nickel amount in copper, the elongation will decrease. Next is strain hardening. So it is the enhancement of strength with increased plastic deformation. The strain hardening is the phenomena whereby a ductile metal becomes harder and stronger as it is plastically deformed. It is also called work hardening or cold working because the temperature at which deformation takes place is lower than the melting temperature. The effects of strain hardening may be removed by annealing heat treatment, slow heating and slow cooling. So if you have deformed your material to a lot of extent and you want to further reduce the size of your material, then in between you can provide some annealing heat treatment. So it is basically heating your material to particular temperature which will lead to relief and relaxation of these dislocations, and it will provide some softening effect. Next is strength increases but ductility is sacrificed. So here you can see, with the amount of dislocation is keep on increasing, then it is proportional to the shear stress of material. Next is precipitation and edge hardening. It is the technique that is used to increase the yield strength of malleable materials such as aluminum, copper alloys and stainless steels. So it is based on changes in the solid solubility with temperature to produce fine particles of an impurity phase which blocks the movement of dislocations in a crystal's lattice. Alloys must be kept at elevated temperatures for hours to allow precipitation to take place, and this time delay is called aging. So here you can see, in the as quenched your material will be in this particular supersaturated state. Okay, so there is solvent, aluminum and copper atoms are there. So after you will be providing some heating, precipitation heat treatment, then these copper will come together and form the precipitate. So these precipitate keep on changing with increasing temperature. The size will change, the coherency will change. Next is corrosion of metals, pilling Bedworth ratio. So for good oxidation resistance, the oxide should be adherent to the surface. So pilling Bedworth ratio, if it is lesser than 1, then the tensile stresses in oxide film, so these will be tensile in nature. So that's why this layer will crack and it will provide to the access to the base metal, and this material will keep on getting corroded and corroded. So the brittle oxide cracks and thus it is unprotective. If this ratio is between 1 and 2, then there will be compressive stresses in oxide film, and this will be uniformly over a metal surface, thus it will be protective. If the spilling bedworth ratio is higher than 2, the high compressive stresses in oxide film and the oxide will crack and flake off, and this layer will be unprotective. So this spilling bedworth ratio is given as volume of oxide formed divided by volume of metal that is consumed in the oxidation. So this ratio is given for various metals. So between alumina and chromium oxide, this is between 1 to 2. Okay, so these are the materials which are safe, which provide better corrosion resistance, which is aluminum, nickel, copper and chromium. That's why steels are always alloyed with the chromium to provide this chromium oxide layer which is impervious. And in case of potassium, sodium, magnesium and iron, these have spilling bedworth ratio which is not between 1 to 2. So these are very poor corrosion resistance. Next is ceramics. So ceramics word is derived from the Greek term keramikos, which means burnt stuff. So clay is the earliest known ceramic which is used for making potteries, and these ceramic materials are inorganic crystalline materials made from compounds of metal and non-metal, primarily held by ionic and covalent bonds. The glass by definition is not a ceramic because it is an amorphous solid, but its mechanical properties behave similarly to ceramic materials. The common characteristics for ceramics is these are hard and brittle. So carbon in form of diamond is the hardest known material, and it is strong in compression. So typically 10 times it is, but it is weak in tension. It is chemically inert, so it provides very good corrosion resistance. Insulators of heat and electricity, except carbon in the form of diamond and graphite. So diamond is insulator of electricity, but it is a conductor of heat, while graphite is conductor of both electricity and heat. Next is high and well defined melting point for ceramics. Next is bonding in ceramics. So many ceramics exhibit a combination of ionic and covalent bonding types, and the degree of ionic character being dependent on the electronegativities of the atoms. In case of ionic ceramics, ionic bonding is predominant. They are compounds of metal with non-metal. The electrostatic attraction between the unlike charges is responsible for dense packing. Examples include sodium chloride, magnesium oxide, zirconium oxide and alumina. Next is covalent ceramics. In case of covalent, bonding is predominant and they are compounds of two non-metals or occasionally pure elements such as diamond. The bonds are formed by sharing electrons with their neighbors to give a fixed number of directional bonds. Examples include silica, graphite, diamond, etc. Next chapter was polymers. So in case of polymers, firstly we saw the classification. So based on molecular structure, you have linear, branch, cross-linked and network type of polymers. Based on origin, you have natural and synthetic type of polymers. Based on polymerization reaction, you have chain polymerization and step polymerization. And in case of next, based on thermophysical behavior, we have thermoplastics and thermosets. Based on end use of application, plastics, elastomers, fibers, coatings, adhesives, films and foams. Next is advanced polymers such as ultra high molecular weight polyethylene and liquid crystal polymers. The classification based on molecular structure. So first is linear. In this, units are joined together end to end in single chains, and maybe some weak van der Waals and hydrogen bonding between the chains can be present. These are soluble and fusible. Examples include high density polyethylene, polyvinyl chloride, polystyrene, and nylon polymethyl methacrylate PMMA. Next is branched. In this case, you have side branch chains which are connected to main ones. These are more soluble and fusible, and example include low density polyethylene. So in this case, these branches will prevent these main chains to come very closer, so the density will reduce because of these empty spaces, because of these branches. Next is cross-linked. So in this case, adjacent linear chains are joined one to another at various positions by covalent bonds, and these are insoluble and infusible. Next is network. In this case, you have high cross-linking and 3D network. These are insoluble and infusible. Examples include rubber, polyurethanes, and phenol formaldehyde. Classification based on thermophysical properties. First is thermoplastics. These are heat sensitive, so they soften and flow upon heating, and these remain soluble and fusible under many cycles of heating and cooling. Thus they are recyclable. Most linear polymers and those having some branched structures with flexible chains are thermoplastics. Individual polymer molecules are held together by weak secondary forces, van der Waals forces, hydrogen bonds, and dipole-dipole interaction. These are easy to repair by welding, solvent bonding, etc. The unlimited shelf life, they won't undergo polymerization during storage or in processing unit. Disadvantages include they are prone to creep. Examples: polyethylene, polystyrene, polyethylene terephthalate, and PVC, nylon polypropylene, and PMMA. In case of thermosets, thermosetting polymers are network polymers. They are creep resistant, so they are less sensitive to temperature. They attain permanent hardness due to cross-linking and then do not soften and flow upon heating. These are non-post formable. They are obtained in a soluble or fusible stage in the early or intermediate stage, but once they get cured, they will be infusible and insoluble. These are excellent thermal and chemically stable once they are polymerized. Disadvantages include that they are brittle and non-recyclable. Examples include bakelite, epoxy, and urethane. Curing of thermosets. So curing is the process of to transform thermosetting resin, soft, solid, or viscous state into an infusible, insoluble polymer network under heat and pressure. Viscosity of the system rises until gelation occurs. At this point, two phases exist, a gel phase and a sol phase. The gel phase is the gel part. The sol phase can be extracted with solvents. The amount of sol phase present decreases as the reaction progresses further. Upon further reaction, vitrification, hardening occurs. So these are the steps: monomers, then viscosity increases, gelation, and vitrification. Next is addition polymerization reaction. So in this case, monomer units are attached one at a time in a chain-like fashion to form a linear macromolecule. These are characterized by the presence of a few active sites which react and propagate through a sea of monomers. These are used for the synthesis of thermoplastics. So first reaction is initial decomposition. So your catalyst will turn into two radicals, 2 times R star. This chain initiation, this radical will react with the monomer and R plus M1 star. Then this chain will propagate, it will keep on reacting with monomers and keep on attaching. Then finally chain termination, these two R will be here and these will be connected. Next is condensation polymerization reaction. It involves more than one monomer species. Monomers can react with any nearby monomer and no special activation is needed to allow a monomer to react. There is a small molecular weight byproduct such as water or ammonia that is eliminated or condensed. Typical reaction is, in this case, it is HOROH. So this H with OH, it will come out as H2O and this chain will start to propagate. Second step, then it will be keep on forming, and the thermosetting polyesters, phenol formaldehyde, the nylons, the polycarbonates are produced by condensation polymerization. Next is advanced polymers. So ultra high molecular weight polyethylene. It is linear polyethylene that has an extremely high molecular weight and trade name is Spectra or Dyneema. An extremely high impact resistance will be there and outstanding resistance to wear and abrasion. These also have a very low coefficient of friction and have a self-lubricating and non-stick surface. These have very good chemical resistance to normally encountered solvents and these have excellent low temperature properties. These also have outstanding sound damping and energy absorption characteristics. Demerit includes mechanical properties diminish rapidly with increasing temperature. Degree of polymerization. So in this case, Mn bar divided by M, where Mn is the number average molecular weight divided by M repeat unit molecular weight. So it will tell you how many molecules are in one particular this polymer. So example, suppose for polyvinyl chloride, Mn is the molecular weight is 21,150 gram per mole. Then repeat unit molecular weight you can calculate for PVC with the formula, it will be 62 gram per mole. So it will have 341 units in polymer. So this is the degree of polymerization. So if you keep on increasing the degree of polymerization, your melting temperature will keep on increasing. Next is polydispersity index. It is the larger the polydispersity index, the broader the molecular weight. So the monodispersed polymer where all the chain lengths are equal, such as a protein, it has this polydispersity index as 1. In case of step polymerization reactions, typically yields value with 2, and for chain polymerization, this value is 1.5 to 20. So it is just the ratio of the this weight average molecular weight divided by number average molecular weight. Next is copolymers. So when there is more than one type of mer present, the molecule is a copolymer. The copolymers are a common type of material used commercially. Examples of copolymers are ABS, polyethylene vinyl acetate, and nitrile rubber. Copolymerization is the method by which a copolymer is created from various types of monomers, and it is frequently used to enhance or change particular characteristics of plastics. Some types of copolymers are graft copolymers and block polymers. and alternating copolymers. So here alternating, this will be AB type. In random there won't be any repetition or anything. In block there will be blocks of A and blocks of B. Next is physical state of polymers. So classification can be, they can be partially crystalline state, viscoelastic state, or highly elastic state, which is rubbers. It can also be in glassy state. So in this case, organic glasses from polystyrene, polymethyl methacrylate, polyvinyl chloride. So in case of liquid, polymers will look like this, and after these cannot be go to the perfect crystalline, but there can be some crystalline regions. So they won't be 100% crystalline. They will never be 100% crystalline, but there can be some percentage of crystallinity in these polymers. So crystallinity. So firstly, crystalline region, it is orderly arrangement of molecular chains. In case of high crystallinity, means higher density, more strength, and higher resistance to both dissolution and softening by heating. The density of crystalline polymers is higher than amorphous polymers due to close packing. The degree of crystallinity in polymers, so it ranges from completely amorphous to about 95% crystalline, but never 100% crystalline. The metal specimens are almost always entirely crystalline. Ceramics are either totally crystalline or totally non-crystalline. So these are the regions where crystalline regions are there, and these are always surrounded by amorphous regions. Crystallinity in polymers. So degree of crystallinity is affected by rate of cooling during solidification. So in case of rapid cooling, time of alignment will be less and crystallinity will be less. Next is chain configuration. More the side branching and cross linking, more the restriction to prevent the chain alignment, and lesser will be the crystallinity. Thus linear polymer have high degree of crystallinity. Most network and cross-link polymers are almost totally amorphous. Crystallinity in polymers. So examples of highly crystalline polymers: polypropylene, nylon, Kevlar, and Nomex. Examples of highly amorphous polymers: so polymethyl methacrylate, polycarbonate, and polyisoprene. So these are the highly amorphous polymers. Percent crystallinity can be given with this formula, where rho C times rho S minus rho A divided by rho S times rho C minus rho A. Here rho S is the density of specimen, rho A is the density of totally amorphous polymer, rho C is the density of perfectly crystalline polymer. Next is tacticity. It is the for different atomic configurations for the same composition. So when you have pendant atoms, pendant groups, then such as benzene and others, so how they provide configuration to your material, it will provide some change in some characteristics or some properties of materials. So tacticity is the way pendant groups are arranged along the backbone chain of a polymer. In case of isotactic and syndiotic, the regular geometric facilitates the fitting of adjacent chains, thus more crystalline. In case of atactic, these are poorly crystalline due to irregularity of side group. In also larger the side bonded groups of atoms, lesser will be the tendency for crystallization. So this is the isotactic, this is syndiotic, and this is atactic type of system. Next is glass transition temperature. Definition. So the temperature at which polymer experiences a transition from rubbery to rigid state. Below Tg, the polymer becomes hard and brittle like glass due to the reduction in the motion of large segment of molecular chains with decreasing temperature. Tg is different for each polymer. Glass transition happens only to polymers in the amorphous state. So here you can see with increasing temperature there will be a glass transition and there will also be crystallization at melting temperature, and this Tg will be lesser than melting temperature. So these are glass transition temperatures for polyethylene. It is minus 110 degrees C. For polyfluoroethylene it is minus 97, and so on. Next is factors affecting Tg. So chain length. Tg is proportional to the molecular weight of the polymer. Chain stiffness increases if the double bonds are there, aromatic groups, bulky or large side groups are present, and it will increase in Tg. Plasticizers. So addition of plasticizers also reduces Tg, and cross-linking also reduces chain mobility. So Tg will be increased. Copolymers. Tg will be based roughly on the weight fraction of each material present in the copolymer. Next is effect of temperature on polymers. So here with increasing temperature you can see elastic modulus will decrease, but with the percent crystallinity, if it is increasing in this way, then this decrease will fall slower compared to this amorphous materials. And in case of this is elastic modulus again and increasing cross linking, so this will lead to this type of behavior. Next is viscoelastic deformation. An amorphous polymer may behave like a glassy polymer at low temperature, a rubbery solid at intermediate temperatures above Tg, and a viscous liquid as the temperature is further raised. For intermediate temperatures, the polymer is a rubbery solid showing viscoelastic behavior. So here you can see if you are applying load at Ta and releasing load at Tr, then the strain will also be, if it is identical, then it is for totally elastic materials. And if the after application the strain is keep on increasing, then this is for the viscoelastic materials. And if it is totally viscous, then as soon as you start applying load, then your material will keep on deforming, and after releasing there won't be any recovery in the strain. Next is fracture in polymers. So stress strain curve can be seen here. So for low fracture strength compared to metals and ceramics, fracture mode, they have low fracture strength compared to metals and ceramics, and the fracture mode in thermosetting polymers is for highly cross-linked, they are brittle, and fracture mode in thermoplastic materials, they are both brittle and ductile are possible. Crack forms at the region of localized stress concentration such as scratches, notches and sharp flaws. The factors which favor brittle fracture are temperature reduction, increase in strain rate, sharp notch presence and increased specimen thickness. So these are the stress strain curves. You can see for soft and flexible they are very ductile, but the strength is very low, while for brittle materials the ductility is very low. These are rigid and brittle, so melamine and melamine phenolic, these are some of the examples. Then for tough and brittle, it is ABS and nylon, which will be showing good ductility as well as good strength. Fracture in polymers. So amorphous thermoplastics, so below Tg they are brittle, they have low fracture resistance, and above Tg they are ductile, they have high fracture resistance. The plastic yielding prior to fracture, and the fracture phenomena is known as crazing. In this case, crazes are the regions of localized plastic deformation. In this case, it forms at highly stressed region associated with scratches, flaws and molecular inhomogeneities. It leads to the formation of small and interconnected microvoids. Region between microvoids act as fibrillar bridges, and under load these fibrillar bridges they elongate and break. These microvoids they grow and merge. Thus the crack propagates perpendicular to the applied tensile stress. Fatigue. So polymers can undergo fatigue failure under cyclic loading. Fatigue behavior is more sensitive to loading frequency than compared to metals. High frequencies and the relatively large stresses can cause localized heating which softens the material leading to failure. So these are the fatigue properties of some of the materials. So PET and PS, these are the ones having good performance compared to other PP and PE. Next is factors affecting mechanical properties for polymers. So first is temperature. So as you keep on increasing temperature, you can see stress strain curve is changing. So your material is becoming more lesser of strength and more of ductility. So your material is becoming tougher. So an increase in temperature produces decrease in elastic modulus, reduction in tensile strength and enhancement of ductility. If you are increasing molecular weight, for many polymers, tensile and impact strength increases with increasing molecular weight due to increased chain entanglements. Viscosity also increases. Next is degree of crystallinity. So higher the crystallinity, higher the close packing. So it will be having higher density, more strength and higher resistance to both dissolution and softening by the heating. Next is cold drawing. So it is analogous to strain hardening in metals. It is used in the production of fibers and films, and molecular chains become highly oriented. The properties of drawn material are anisotropic and perpendicular to the chain alignment direction, and strength is reduced. So here you can see as you keep on applying the tensile stress, these chains will start to get highly oriented, and in this particular direction your material strength will keep on increasing, and after particular stress it will fracture. And this is the part where it is called cold drawing. Next are composites. So in case of composites, classification is it can be particle reinforced. These particles can be large particles, or dispersion strengthened where particles will be small. It can be fiber reinforced or it can be structural. In case of structural, you have laminates, and these can be sandwich type of structure or it can be simply laminates with the orientation either unidirectional or cross ply. Large particle composites. So examples include concrete, which is composed of cement. Cement acts as matrix, and the sand and gravel it acts as particulates. The particulate phase is harder and stiffer than matrix, and the reinforcing particles they tend to restrain the movement of the matrix phase in the vicinity of each particle. The matrix transfers a fraction of applied load to the particles, and the improvement of mechanical behavior depends on the strong bonding at the matrix particle interface. So cement plus sand, stones and water combined will be giving you concrete. Next is dispersion strengthened composites. So the particles are normally much smaller with diameter between 10 to 100 nanometer. Strengthening occurs on the atomic or molecular level. The matrix bears the major portion of the applied load, while the small dispersion particles hinder the motion of dislocation. Thus plastic deformation is restricted such that yield and tensile strengths as well as hardness improves. Examples include sintered aluminum powder, which is flakes of aluminum coated with alumina. which are dispersed within an aluminum metal matrix. So here you can see this dislocation will be hindered because of this particular strong particle which has elastic modulus higher than matrix. So these dislocations will be stopped because of this strain field. Next is fiber reinforced composites. These on the basis of diameter and character, fiber phase can be grouped into whiskers, fibers and wires. In case of whiskers, they are very thin single crystals that have an extremely large L upon D ratio, but they have the form of fibers. The flow free and thus extremely high strength, but they are expensive, include graphite, silicon carbide, silicon nitride and aluminum oxide, etc. Fibers, these are material that has at least L by D ratio equal to 10:1. These are either polycrystalline or amorphous, generally polymer and ceramics. Next is wires. These are relatively large diameters, and typical materials include steel, molybdenum and tungsten. Next is the role of matrix in composite includes binding fibers together, protecting the individual fiber from damage by the external environment, act as the medium to transmit and distribute externally applied stress to fibers, serves as a barrier to crack propagation. The role of fibers, they enhance the stiffness, enhance strength and provide crack bridging and enhance thermal resistance. Requirements of composites, the matrix material should be ductile, elastic modulus of the fiber should be much higher than that of the matrix, and there should be adequate bonding between the matrix and fibers. Metal matrix composites. So the matrix is ductile metal, usually alloys of aluminum, magnesium, titanium and copper. Fibers include carbon, silicon carbide, boron, aluminum oxide, etc. Advantages over PMC include that they have higher operating temperatures, non-flammability, greater resistance to degradation by organic fluids, and demerit includes MMCs are costlier compared to PMCs. Next is PMC, polymer matrix composite. Here glass fiber reinforced polymer composites. So in this case matrix will be plastic, most often epoxy and polyester resin. Reinforcement will be glass fiber or E-glass, which has diameter from 3 to 20 micrometer. Typically 55% silica, 16% calcium oxide, 15% alumina, 10% boron oxide and 4% magnesium oxide. They are easily drawn into high strength fiber from the molten state. Limitation has the service temperature is up to 200 degrees Celsius, above which polymer matrix start deteriorating. Applications include automotive and marine bodies, plastic pipes, storage containers and industrial flooring. And GFRP, so these are the properties that are given. Next is ceramic matrix composites. So ceramics are highly brittle in nature. They have low fracture toughness. In general, the fracture toughness of ceramics is 1 to 5, while metals are 20 to 90. By using CMC, fracture toughness can be increased to lie in the range of 2 to 6 to 20 MPa under root M. So crack initiation normally occurs within matrix phase, whereas crack propagation is hindered by particles, fibers and whiskers. These exhibit improved high temperature creep behavior and resistance to thermal shock. Next is smart materials. So smart materials, these are also called intelligent or responsive materials, which are design materials that have one or more properties that can be significantly changed in a controlled fashion by external stimulus such as stress, moisture, electric field, magnetic field, light, temperature, pH and chemical compounds. Some of the features. So these materials are part of the group of materials broadly known as functional materials. The basic energy forms that get interchanged are thermal energy, electric energy, magnetic energy, sound energy and mechanical energy. It is analogous to biological materials, adaptivity, cellular function, self-sensing, actuation and control. Smart sensors and actuators are highly embeddable. First is direct effect. So all piezoelectric materials and PVDF, polyvinylidene difluoride, magnetostrictive materials, optical fibers, these are provide direct effect in which stress is converted into electric potential, and these are used in making sensors. Converse or reverse effect. In this case, ferroelectrics, perovskites, piezo ceramics, PVDFs respond to electric field by change in shape. Terphenol D amorphous matte glasses show a similar effect with change in magnetic field. Shape memory alloy respond in a similar manner but with the change in thermal field. The rheological fluids, they respond to electric magnetic field by changing its viscosity. So in this case, previously stress was applied and electric potential was obtained, while in this case electric magnetic thermal stimulus is applied and this converts it into strain. So this is reverse effect where it is used for making actuators. And why smart sensor and actuators? These provide real-time response, they exploit functional properties, better embeddability, minimum effect on the structural properties, reduction in weight, less power consumption and better reliability. Now the smart materials in nature. So pine cone in water. When submerged in water, pine cone changes its shape and retracts itself. As best weather for planting pine trees is when it is warm and dry. So when it's cold and wet, pine seeds can disperse in the wind because of the hygroscopic material found underneath pine spikes, a smart material that absorbs moisture and expands. Smart material in history, pyramids of Giza. So a self-healing material, lime mortar, a concrete-like material is used to construct these. It heals itself when a crack develops by a reaction with the moisture and carbon dioxide present in the air and forms limestone, and that limestone grows into the crack and completely heals the material. Next is first time smart materials came to notice when piezoelectric effect was discovered in 1880. Two French physicists, brothers Pierre and Paul Jacques Curie, in crystals of quartz, tourmaline and Russell salt, potassium sodium tartrate, they found this piezoelectricity, and they took the name from the Greek word piesin, which means to press. And these are various smart materials and their inputs and outputs. So in case of piezoelectric, the deformation is converted into potential difference. Thermochromic materials, temperature is converted into color change. Photochromic materials, radiation is converted into color change. Shape memory alloys, temperature converted into deformation. Electrostrictive, potential difference converted into deformation. Magnetostrictive, magnetic field is converted into deformation. Thermoelectric, temperature is converted into potential difference. So these are again, most are repetition, but in case of piezoelectric material, you can convert stress and electric field into electric charge and mechanical strain. In shape memory alloy, heat is converted into original memorized shape. Electrorheological fluid, electric field converted into change in viscosity, internal damping. Magnetostrictive material, magnetic field converted into mechanical strain. Now in piezoelectric materials, electricity from pressure was discovered, and the piezoelectric materials convert electrical energy to mechanical energy. They can be used as actuators. They provide a voltage to create motion. Sensors such as many accelerometers and energy harvesters, since the charge generated from motion can be harvested and stored. Applications include BBQ igniters and actuators for inkjet printer heads, energy harvesters, sonar equipment, ultrasonic cleaning and flow control devices. And this is the piezoelectric behavior that is seen in quartz. So with the tension, the distribution of charges becomes like this, and in compression it changes. So piezoelectric effect can be of two types. Direct piezoelectric effect, where compressive stress along the polarization direction generates a voltage of the same polarity as the Pauling voltage. And in converse or reverse piezoelectric effect, the voltage of the same polarity as the Pauling voltage causes an extension along the Pauling direction and contraction perpendicular to the Pauling direction. Now the equation for piezoelectric effect. So in case of direct effect, D equal to dx plus epsilon E. For converse effect, x strain is equals to Sx plus dE. So here capital X is stress, small this d is the electric displacement, S is compliance, capital E is electric field intensity, E is permittivity, D is piezoelectric constant. Next is magnetostrictive materials. So in 1842, James Prescott Joule noted that a ferromagnetic sample changed its length with the application of magnetism and magnetostriction in materials due to domain migration and reorientation under applied magnetic field H. If a crystal of ferromagnetic material is initially in a compressed state, the effect of magnetostriction becomes more pronounced. All ferromagnetic materials show magnetostriction to different degrees. It is observed that a maximum one can achieve is for cobalt, which saturates around 50 microstrain ppm. Okay, so in absence of any external magnetic field, this is what the domains look like, and if you apply this magnetic field, then these align and it leads to expansion in material. So in general, large force, deflection and energy conversion efficiency, and they do not decay with time. Magnetostrictive transducers are cost effective in the low frequency band and could be effectively used for deeper sea measurement due to superior mechanical properties. Joule effect, in this case your epsilon equal to SH sigma plus dH. For Villari effect, B equals to D sigma plus mu sigma H. Here B is magnetic flux density, H is the magnetic field intensity, D is magnetostrictive constant, SH is compliance matrix of the material at a constant magnetic field, mu is the permeability of material at constant stress. So these are various materials and their magnetostriction. For iron it is 14, for nickel it is negative minus 33 ppm, for cobalt it is 50, for permalloy it is 27, and for DyFe2 it is 650, and so on. For smart polymers, polymers that respond to external stimuli by changing shape and size are known as active smart polymers, and these are of two categories: active polymers, which respond to external stimuli such as pH, magnetic field and light, example PAC, polyanionic cellulose. Electroactive polymers, these respond to the change in the electrical input, also known as EAP. EAPs respond to electric stimulus are broadly classified into two groups: electronic EAP which is driven by electric field or Coulomb forces. Ionic EAP, which change shape by mobility or diffusion of ions. Now differences electronic and ionic EAPs. So in case of electronic, it needs high activation voltage, more than 150 volt per micrometer, and for ionic EAP they require low driving voltages 1 to 5 volt. For electronic EAP they have high energy density and rapid response time in milliseconds. For ionic it is relatively slow response time, but the amount of deformation is more. They performs better under wet conditions. Dielectric EAP, electrostrictive paper, ferroelectric polymers and liquid crystal elastomers, some are the examples. Ionic polymer gels, ionic polymer metal composites, conducting polymers, carbon nanotubes are some of the examples of ionic EAPs. Next are thermochromic materials. So thermochromic materials change color reversibly with change in temperature. They can be made from semiconductor compounds, liquid crystals or metal compounds. The change in color happens at a determined temperature, which can be varied by doping the material. Applications, they are used to make paint, inks, or are mixed to molding, for casting, materials for different applications. So here you can see liquid crystals are closer together than this wavelength of the blue reflected light, and if the liquid crystals are further apart because of the temperature, then these will be providing red reflected light. Next are photochromic materials. So photochromic materials change reversibly color with changes in light intensity. Usually they are colorless in a dark place, and when sunlight or ultraviolet radiation is applied, molecular structure of the material changes and it exhibits color. When the relevant light source is removed, the color disappears. Applications include sunglass, data storage, novelty items, smart windows, solar energy storage, etc. So as in the daytime, this material will be due to the photons, it will act as shield for window, while in case of night time there won't be any photons, so it will be transparent. So it will be useful in making windows and sunglasses. So trans-azobenzene, you can see with the application of this photon, it changes its configuration from trans to cis, which leads to change in color. Next is shape memory alloy. Okay, so a shape memory alloy is an alloy which can be deformed when cold, but it returns to its pre-deformed shape, remembered shape, when it is heated. It may also be called memory metal or memory alloy, smart metal, smart alloy, or muscle wire. A mix of roughly 50% nickel and 50% titanium is the most common shape memory alloy, known as nitinol, which was originally developed by the Naval Ordnance Laboratory. Copper, zinc, aluminum and copper, aluminum, nickel are also widely used. So in this one you can see, as this wire, when it's dropped in hot water, it regains its original shape, and when it is cold it is deformed, but it doesn't remember this shape, but it remembers the initial shape. Principle, so ability to remember its austenite phase. As the metal is cooled to the martensite phase, it can be easily deformed, and when the temperature is raised to the austenite phase, it reforms to the original shape of the material. Pseudoelasticity, when the metal is changed to the martensite phase simply by strain, the metal becomes pliable and can withstand strains of up to 8%. The advanced materials still under development include magnetically activated shape memory alloys. And here you can see with the austenite, if it's cooled and then it's twinned and deformed, then again when it is heated it regains its original shape. Shape memory effect. So certain classes of metallic alloys, they have special ability to memorize their shape at a high temperature and recover large deformation imparted at a low temperature or thermal activation. So the recovery of strains imparted to material at a lower temperature due to heating is called shape memory effect. This was first discovered in 1932 in gold cadmium alloy. Three types of shape memory alloys that are currently popular are copper zinc aluminum, copper aluminum nickel, and nickel titanium. The last one is commercially available as NPTEL, NOL, Naval Ordnance Laboratory from USA. Manufacturing. These shape memory alloys are typically made by casting using vacuum arc melting or induction melting, and these are specialized techniques which are used to keep impurities in the alloy to a minimum and ensure the metals are well mixed. The ingot is then hot rolled into longer sections and then drawn to turn it into wire. Problems with shape memory alloys. So fatigue from recycling, it causes deformations and grain boundaries. It begins to slip along planes and boundaries. Overstress, a load above 8% strain could cause the shape memory alloys to completely lose its original austenite shape. Difficulty with computer programming and more expensive to manufacture compared to steel and aluminum, and relatively new. Some of the potential applications of smart materials. So self-healing asphalt, self-healing concrete, so your roads can heal itself, your concrete or walls can heal itself. Self-healing coating, so if you're providing oxidation resistant coating or some coatings to material, if it self-heals, then your material will remain protected, base material or substrate. Orthopedic surgery, smart aircrafts, these are some of the applications. In smart fabrics, intelligent glasses, so as we saw earlier, thermochromic or photochromic materials, they can be used in making intelligent glasses. Robotics, smart skin for submarine, smart bridges, so in bridges also you can provide these piezoelectric materials for generation of electricity and for storage of electricity. These type of materials can be used, and various sensors also, sensors and actuators, these also use smart materials. Now the merits of using smart materials, these have good mechanical properties and they have biocompatibility as well, so they can be used for making sensors which can be embedded in human body as well. Next is simplified packaging and compactness, safety mechanism, high energy density, durability and reliability, excellent bandwidth and self-repaired. So in case of self-healing materials, they can get self-repaired as well. And high energy density, the sensors that are made using these smart materials, they have high energy density. And also these applications are mainly in making actuators, then orange is for sensors, then for making transducer, then to some extent in making structural applications and in other. Demerits include they are more expensive compared to your traditional materials such as steel, aluminum, and these are not easily available in market, and also they have low energy efficiency, and complex control is also there to understand, and highly sensible to require more care while storage. So they are as we know, these smart materials are sensitive towards pH, humidity and other type of atmospheric parameters, so their storage becomes very uh, typical, very critical. Next is environmental pollution. So some of these materials, they consist of heavy elements, so these, their after their use, after, so recyclability is also a challenge and they become pollution and they become reason for environmental pollution. Long term effects are also unknown. Next are the non-mechanical properties of materials. So this was the last chapter. So first property is thermal property. So thermal properties, they describe the response of a material to the application of heat. As a solid absorbs energy in the form of heat, its temperature rises and its dimensions increase. It is important for thermal properties are heat capacity. Some of the important thermal properties are heat capacity, thermal expansion, thermal conductivity. So this is the heat capacity of various materials. So as we can see, for polypropylene 1925, polyethylene 1850, polystyrene it is 1170, Teflon it is 1050. For ceramics, magnesia it is 940, for aluminum 775, glass 840, for aluminum 900, steel 486, tungsten 138 and gold 128. So here we can see polymers have significantly larger Cp because covalent bonds in polymers do not let atoms exchange electrons as metallic bonds do. Next is heat capacity represents the amount of energy that is required to produce a unit temperature rise, indicative of a material's ability to absorb heat from the external surroundings. Mathematically, this heat capacity can be written as energy change gain or loss dq divided by dt, which is resulting temperature change. So here you can also see with increasing temperature your heat capacity of material will keep on increasing. Cv is 0 at 0 Kelvin. So heat capacity, your increase with temperature, it increases with temperature, and for solids it reaches a limiting value of 3R. R is the gas constant. And from an atomic perspective, energy is stored as atomic vibrations. And as temperature increases, the average energy of atomic vibrations also increases. Next is thermal expansion. So temperature of a solid is a measure of its potential energy, and most solid materials expand upon heating and contract on cooling. So the heating to successively higher temperatures raises the vibrational energy. Thus the interatomic separation increases from R0 to R1 to R2 and so on. The greater the atomic bonding energy, the deeper will be this curve. So deeper will be meaning it will be having higher elastic modulus. So for ceramics it will be deeper, and in that case it will be having lesser of the thermal expansion. So narrower is this potential energy trough will be, and the increase in the interatomic separation with a given rise in temperature will be lower. So for these materials we can see that polymers have highest 50 to 400 alpha 1, meaning thermal expansion coefficient, and for metals it is 5 to 25, and for ceramics it is in between 0.5 to 50. For ceramics it is least 0.5 to 15, then higher will be for metals, then highest for polymers. Next is thermal conductivity. So thermal conduction is the phenomena by which heat is transported from high to low temperature regions of a substance, and Fourier law states that the steady state, the heat flux is directly proportional to a temperature gradient. So Q upon A it will be equal to minus K dt upon dx, where K is the thermal conductivity in watts per meter Kelvin. Negative sign here indicates that the flow in the direction of the decreasing temperature. Heat flow is in the direction of the decreasing temperature. The thermal conduction in a solid takes place by both lattice vibration waves, phonons, and free electrons. Thus, total conductivity is addition of lattice because of the lattice vibration and because of free electrons. Metals are extremely good conductors of heat because relatively large number of free electrons exist that participate in thermal conduction. The purest form of metal will have high conductivity than alloy form, and in the alloy different atoms will have different electron affinity. Thus movement of the excited electrons becomes hard. Since free electrons are responsible for both thermal and electrical conduction in pure metals, the two conductivities are related by Widman-French law as L equals to K upon sigma T. L is the Lorentz constant, 2.45 times 10 to the power minus 8. K is thermal conductivity, sigma is electrical conductivity, T is absolute temperature. And this is the thermal conductivity for various materials. For silver it is highest, then copper, gold, and aluminum. Ceramics, they are thermal insulators as they lack large number of free electrons. Thus phonons are primarily responsible for thermal conduction. Also, the phonons are not as effective as free electrons in the transport of heat energy due to phonon scattering by lattice imperfections. The room temperature thermal conductivities range between approximately 2 to 50 watt per meter Kelvin. Amorphous ceramics have lower conductivities than crystalline ceramics as the atomic structure is highly disordered and irregular. Higher porosity also reduces conductivity due to the presence of still air in pores. Thermal conductivities for most polymers are of the order of 0.3 watt per meter Kelvin. The energy transfer is accomplished by vibration and rotation of the chain molecules. Magnitude of the thermal conductivity depends on the degree of crystallinity, and high crystalline and ordered structure means effective coordinated vibration and higher thermal conductivity. So here you can see highest thermal conductivity is for metals, then it is for ceramics, then lowest is for the polymers. Next is thermal stresses and shock. So thermal stresses are the stresses induced in a body when due to change in temperature the deformation is hindered. Thermal stresses in a constrained body will be of compressive nature if it is heated, and vice versa. Thermal shock if the dimensional change is in a material or non-uniform, then it may lead to the fracture of brittle materials like ceramics, which is known as thermal shock. The capacity of a material to withstand thermal shock is defined as thermal shock resistance, TSR, and it is given as this formula. For high thermal shock resistance, a low value of thermal expansion coefficient and elastic modulus E is desired, and a high value of thermal conductivity K and fracture strength sigma F is desired. Electric properties. So from Ohm's law, V is proportional to current. So proportionality constant will be resistance. Here V is voltage drop in volts, I is current, amperes, R is resistance of materials. So materials electric resistance is an extrinsic property which depends on the object geometry. Resistivity is independent of specimen geometry, but it is related to R through the expression R equals to rho times L upon A, L being distance between voltage measuring points, A is cross-sectional area perpendicular to the direction of the current. Unit of rho will be ohm meter. Now electrical conductivity is indicative of the ease with which material is capable of conducting an electric current. So it will be inverse of the resistivity. And on the basis of conductivity, solid materials can be classified as conductors, semiconductors and insulators. Metals are basically conductors and these others are insulators. Electronic and ionic conduction. In case of electronic conduction, current is arising from the flow of electrons. On ionic, current will be arising from net motion of charged ions. Next is effect of temperature on metal conductivity. So increasing temperature causes greater electron scattering due to increased thermal vibration of atoms. Hence the resistivity of metals increases or conductivity decreases linearly with temperature. The total resistivity of metal is the sum of contributions from thermal vibrations, impurities and plastic deformation. So scattering mechanism, they act independently of one another. In case of insulator, they have wide band gap more than 2 electron volt. So there are very few electrons that get excited across band gap. For semiconductors, they have narrow band gap lesser than 2 electron volt. So there are more electrons that get excited across band gap. Next is magnetic properties. So the magnetic field is a force which is generated due to the energy change in a volume or space. A magnetic field is produced by an electric charge in motion. For example, current flowing in a conductor, orbital movement of a and spin of electron. So origin of magnetic moments will be because of orbital motion around the nucleus and spin of electrons. So that's it from my side.